We'll do today Module 5, Session 5, Logic Synthesis with the Verilog. Here, why? What is logic synthesis? Logic synthesis is the process of converting a high-level description of the design into an optimized gate-level representation given a standard cell library and certain design constraints. It will give you a standard cell library and certain design constraints when you give logic synthesis. A standard cell library can have simple cells such as basic logic gates like AND, OR, and NOR, XOR, NAND, all those things, and also macro cells such as adders, muxes, or special flip-flops we're going to use as a standard cell library. And a standard cell library is also known as technology library. You can write instead of standard cell library, we can use as a technology library. So that is when you do in your lab, we're going to use RTL synthesis, technology, RTL netlist, and also technology library. Also, it is going to shows that and all you had seen, I think. Okay, so this is about explanation I am telling. Standard cell library is also known as technology library. So here earlier when technology library or logic synthesis was doing with a designer's mind only. That is how the flow is going to take. That is explained here. Designer's mind as logic synthesis tool. When you use listener's mind as a logic synthesis tool, how it is going to be, that is here explained. See here, he is going to take a architectural description of the design. What is the design? That entire architectural description he is going to take, and that has to be he is going to divide that into a partitioned into a high level blocks. Partitioning of that high level blocks can be done, and then again here he is going to use his mind, designer's mind is comes in picture here. And here after partitioning, that each partition is going to take and add some design constraints and standard library cells if it is needed, he is going to use that, and then he is going to generate a gate level representation. He will going to get a gate level representation over here, and if it is completed gate level representation, then he will going to check that whether it is meeting a design constraints. If the it is meets that design constraints, he'll proceed to the optimized gate level representation. So this is the flow. If not, the design constraints are not matched, then what is going to do is again going to back to the iteration loops. Design iteration is going to here. Then again, that means partition block is going to once again he is going to take and he is going to use his mind and adding some in constraints, design standard library cells, all those things he is going to take. And then this standard library cell is a technology dependent, it's his own way is going to standards that standard cells, so that will be depend on the technology. Okay, so here again it's going to pitch this. So this is about your designer's mind flowchart. And again when CAD tool comes into picture, here the CAD tool, that the basic computer aided logic synthesis process is like this. Here we are having a same thing, only it is explained in easier manner. That means architectural description is going to take here, and again high level description here, and high level after high level description, here partitioning of that it is not done here. High level description, the next step is high level description is here, and computer aided logic synthesis is doing here. That CAD tool will going to use a computer aided logic synthesis. Here it is using this design constraints, and is going to adding that standard library cells, all those things is going to add here a CAD tool, and again optimized gate level netlist. It here produces a optimized gate level netlist is going to produce here, and here whether if it is meets that constraints, that given constraint, whatever the constraints if we are considering, that is depends on the technology or what are the things it is given, that is going to check here. Suppose it matches, then it goes to the place and route. Place and route, then afterwards it goes to the fabrication process. Otherwise, again it will going to repeat in this process. That is here. No, no means it goes back here. High level description, computer aided logic synthesis, optimized gate level, netlist, and then it will comes to here. So like this, the CAD the logic synthesis process takes place. So this is another flow chart we are having. Then here, when it was there, when both comparing both, what is the drawbacks of designer's mind when he is using, and what is the impact of that? It is explained here. The impact of logic synthesis, that is comparing that both designer's mind and as well as CAD tool. That will have here we are having limitations of the manual design process. Some limitations is there it is producing here, that is shown in these points here. See here, when you are using a manual design process, for large designs, manual conversion was prone to human error. A small gate missed somewhere could mean redesign of entire blocks. It means here a manual conversion was prone to human error. That means whenever you are writing, you are going to do some mistakes. Or if you forgot to write one small gate also, it is going to give you the mean that redesigning of the entire blocks. So okay, and the designer could never be sure that the design constraints were going to be met until the gate level implementation was completed and tested. Till the end of that level, he is not going to sure about that whether the design constraints were going to met or not. Okay, so that is the one limitation is there, and a significant portion of the design cycle was dominated by the time taken to convert high-level design into gates. Significant portion of the design cycle was dominated by the time taken to convert high-level design into gates. So okay, that is also there. And here, if the gate level design did not meet requirements, the turnaround time for redesign of blocks was very high. If the one mistake if you are doing, then in the middle of the process, if you are wanted to check, means it is going to be a very tedious. That means it will take a lot of time to correct where the system has that means design has gone wrong. That has to be we have to check in each and every point. Then that will take a lot of time, very high. That redesign of blocks was very high. And one more thing, it is a very important thing here. If what if scenario were had to verify. What if scenario were hard to verify? For example, that means what is that meaning means if for example the designer designed a block in gates that could never run at a cycle time of 20 nanoseconds. He has designed one block that is for 20 nanoseconds it is running. If the designer wanted to find out whether the circuit could be optimized to run faster at 15 nanosecond. The entire block had to be redesigned. When he is doing this for running faster than that 20 nanosecond, then entire block has to be redesigned. Thus, redesign was needed to verify if scenario. What if scenario? It is going to be redesigned. That means it will take a lot of time to redesigning that. Entire design has to be changed. That was the drawback here. And if the designer could implement a design blocks differently, there was little consistency in the design styles for large designs. This could mean that smaller blocks were optimized but the overall design was not optimal. Okay, if the large design is there means overall design was not optimal for larger designs. Okay, and if the bug was found in the final, the gate level design, the this would sometimes require a redesign of thousands of gates. Okay, then timing, area, power dissipation in library cells are fabrication technology specific. Thus, if the company changed the IC fabrication vendor after the gate level design was complete, this would mean a redesign of entire circuit and possible change in the design technology methodology itself. It is going to changes. That means vendor to vendor, it is going to be company to company. It is going to that is IC fabrication. It's going to changes. So entire design is going to be redesigned, or it is going to design methodology itself. It is going to changes. Okay, and design reuse was not possible. That is design one design is for one methodology, one technology itself. That is there in this manual design process. And designs were technology specific, hard to port, and very difficult to reuse. This is the thing in this manual design process. So when automated logic synthesis tools addressed these problems, so when it is came, that is also addressing some of the problems. That is whatever the problems manual design was there, that has to be addressed by automated logic synthesis. That is high level design is less prone to human error because the designs are described at a higher level of abstraction. That's why it is very less prone. And high level design is done without significant concern about design constraints. High level design is done without significant concerns about design constraint. Logic synthesis will convert a high level design to a gate level netlist and ensure that all constraints have been met. If not, the designers go back and modifies the high level design and repeats the process until the gate level netlist that satisfies timing, area, and power constraints is obtained. Okay. If not, the designer goes back, modifies the high level design, and repeats the process until a gate level netlist that satisfies timing, area, power constraints is obtained. And conversion from high level design to gates is fast. With this improvement, design cycle times are shortened considerably. Here, when you are using conversion from high level design to gates is fast. With this improvement, design cycle times are shortened considerably. What took months before can now be done in hours or days. Within an hour, or we can do in a days, 1 or 2 days only we can finish that. That was when you are doing a manual design, it was taking a months. It will take a months together, but it is now it has to be easier, and so hours are in a days we can finish it out. And turnaround time for redesign of blocks is shorter because changes are required only at the register transfer level. Turnaround time for the redesign of blocks is shorter because the changes are required only at the register transfer level. Then the design is simply resynthesized to obtain the gate level netlist. Okay, the because it is going to take a redesign of blocks is shorter because the changes are required only at the shorter RTL level only. Then the design is simply resynthesized to obtain the gate level netlist. Okay, and what if scenario is also it is reduced here. That is, what if scenario are easy to verify. If high level description goes does not change, the high level description does not change, the designer has merely to change the timing constraints from 20 nanoseconds to 15 nanoseconds and resynthesize the design to get the new gate level netlist that is optimized to achieve a cycle time of 15 nanoseconds. In a resynthesizing only we can do it. That changing the time constraints can be done. And logic synthesis tools optimize the design as a whole. Optimize the design as a whole. This improves. This removes the problem with the varied designer styles for the different blocks in a design and suboptimal designs. Logic synthesis tools optimize the design as a whole. This removes the problem with the varied designer styles for the different blocks in the design and suboptimal designs. Okay, here a bug is found in the gate level design. The designer goes back and changes the high level description to eliminate the bug. Then the high level description is again read into a logic synthesis tool to automatically generate a new gate level description. This is simple as it was very time taking. It is not there in this. It is only eliminate the bug. Then high level description is again read into the logic synthesis tool to automatically generate a new gate level description. And logic synthesis tools allow a technology independent designs. It is technology independent also is there, and high level description may be written about the IC fabrication technology in mind. Keeping that IC fabrication technology in keeping in that mind, we can describe high level description can be right. We can write written without the IC fabrication in mind. Okay, this is about this session and reference I referred Verilog HDL, a guide to digital design and synthesis. It is from IEEE complaint and by Samir Palatkar, forwarded by Prabhu Goyal. Next, this is our team. We who are all working for this. This is first Dr. Rangaraj sir, GSK SJTI Bangalore Chairman, LMS ECS courses, and Professor RS Rekha Madam, HOD EC Department, GEC Chamarajanagar, Dr. Rudrappa K, HOD EC Department. He is from GEC Carpet, moderator for this LMS HDL, LAG HDL, and myself, Leelavati Devi, Assistant Professor, GEC Chamarajanagar. I am a content developer for this. Okay, thank you.